Okay, so as promised, right at the beginning of this lecture course, we're going to end with my favorite Lie group, which is G2. And G2 is the smallest of the exceptional Lie groups, and it is related to the octonions, which are given by the span of E1 up to E7, where all 7 are imaginary units, they all square to -1, and they satisfy this multiplication rule given by this diagram called the Fano plane. So what I want to tell you about today is the algebraic properties of this Lie group, okay? And try to bring together all of the theory that we've learned over this course into one lecture which describes the properties of this group. So the first thing is I need to tell you what it is. So the simplest way to think about it is we just take 7-dimensional Euclidean space and take the usual Euclidean inner product and we take ourselves E1 up to E7 suggestively to be an oriented orthonormal basis of R7. Okay. Now, I've not chosen that notation at random. This gives us a way to identify. This means that we can identify R7 with the imaginary octonions, right? The purely imaginary ones, the ones where you just have an E1 up to E7 in them. And so what that gives you is the notion of a cross product. On R7. So what do I mean by a cross product? I just mean something which is going to be alternating in the two vectors, and it's orthogonal to the vector that you started with. If I take u cross v, it's orthogonal to both u and v, and if u and v are orthogonal, it has the same length as the product of u and v. And so what you do is you just multiply within the octonions and then skew symmetrize. Right. So you don't have, ei squared is -1 anymore. Ei cross ei is going to be 0. Okay. And what this enables us to do is define for us a distinguished 3 form. So this is the definition, the sort of core definition that makes this all work, is we define a 3 form, phi. So this is an element of the third wedge product of R7 dual by the following formula. So I take 3 elements u in E and W in R7, and I have to tell you what is the number that I get when I plug those 3 vectors in, right? Because it's a map from that to R. And the number is you take the inner product of u with v cross w. That's what it is. Okay? So this should not look that surprising to you, because it looks a lot like the scalar triple product, right? The usual one on R3. And it is. It's the 7-dimensional version of the scalar triple product. And so for the same reasons as it's true on R3, this is totally skew, right? If I permute them around, it stays the same. So if I do v, w, u, I get the same answer. Right? So it is indeed a 3 form. So it's not obvious immediately from the definition, but it's true. Yep, go for it.
Sorry, just remind me what you mean when you say 3 form?
Yeah, 3 form means it just takes 3 vectors in R7 and spits out a number so that it's totally skew in the 3 entries. So if I do any permutation, I get the sign of the permutation times the answer. That's what it means by a 3 form. Okay? Yep. So if I swap these two, I get a minus sign, but if I do a cyclic permutation, I get a plus sign. Right. Okay. Now, what I can do is I'm going to introduce some notation. I'm going to let, this is a bit physicsy, but some of you might be like physics. So I'm going to let E1 up to E7 with the raised index be the dual coframe to the E1, be dual to E1 up to E7. And then for notation, and we're going to let EIJ, so if I see a concatenation of upper indices, what this means is that I'm taking the wedge product of EI, wedge EJ, wedge EK. Right. All right, so this is just to simplify my life. And then, given this formula and the Fano plane, you can actually write down explicitly what phi is. It's E123 plus E145 plus E167 plus E246 minus E257 minus E356 minus E347. So that's what it is. If you just look at that diagram and that formula, then you can write it down explicitly. Now, the nice thing that you can do, and it's based on this formula, so I've given you an explicit formula. There's an interesting fact, which is the following. Well, it's easy to compute, so it's a fact, is that phi, if I just give you phi, this actually determines the inner product. Okay, so that's not very obvious, but I'm going to explain why, and hence the cross product. So actually, although I needed two things to define phi, phi actually recovers both. And the reason is the following. So you'll have to tell me what your notation was from differentiable manifolds, but suppose I have u and v vectors in R7, then how do you denote interior product with a vector? Do you write IU or do you write hook? Huh?
Like iota.
Iota, yep, okay. So let's do that. Iota u phi. So this means something to you, right? This means I put u in the first entry in phi. That's what it means. Okay, so if I do IU phi, and I wedge it with IV phi, and wedge it with phi again, okay, all right, what's going to happen? Well, this is going to be a 2 form, this is going to be a 2 form, this is going to be a 3 form, this is a 7 form. But there's only one 7 form in 7 dimensions, that's the volume form. It's the only thing it could be. It has to be some multiple of the volume form. That's the only thing it could be. And then the multiple turns out to be 6 times the inner product of u and v. So if you just give me phi, I can recover the inner product. That's the reason. Okay. And so this enables us to define what G2 is. So the definition now of what G2 is G2 is going to be, yes. So what I want to say, one more thing, is if we have rho, the induced representation rho of GL7R on 3 forms is, this is a reminder, right? If I take a matrix A, I want to say what it does to phi, right? And it has to spit out some other 3 form. Right? That's what it's supposed to be. It's supposed to be representation. So what this is for all A in GL7R, for all UVW in R7, then what is it going to be? It's just you do phi and you put A's everywhere. Okay, so that's the obvious thing. And then one more thing, just before I give the definition. So the definition is here, but let me just remind you that what is the, and then the derivative sigma of rho at the identity. So that's sigma of x of phi acting on UVW is phi of XUVW plus phi of UXVW plus phi of UVXW. Is that okay? And this is for all x's in the Lie algebra, GL7R. So just 7 by 7 matrices. Is that okay? So that's just, if I differentiate that formula, it's like product rule, right? I'll differentiate the first one, plus differentiate the second one, plus differentiate the third one. So we've seen this before, but I'm just reminding you of the formula. Okay, so now I can tell you what G2 is. G2 is nothing other than the set of elements in GL7R such that if I act by A on phi, I have to get phi. Okay. So that's what it is. Okay, make sense? So what we're saying is that it's the stabilizer of phi. Right. Remember this groups. I mean, we're doing group theory, right? So we should remember what stabilizers are. So this is the stabilizer of phi, and what we see is that because of this fact that I said that if you preserve phi, then that's exactly the same as preserving the cross product, right? So in fact, what this tells you is that G2 is in fact the automorphism group of the imaginary octonions. It's the set of things that preserves the octonionic structure. And because if you're preserving the octonionic structure, you have to preserve the unit, it's the same thing as the automorphism group of the whole octonions. Because if you preserve the unit, you have to do that if you're in the automorphism group of the octonions. So it's just the same thing as being the automorphism group of the imaginary octonions. This is just one and the same thing. So yeah, so this is somehow the slickest way to define G2 as the automorphism group of the octonions, but it's not very practical to work with this definition. It's more practical to work with this fact that it's the stabilizer of the three form. And then we let G2, which should be the Lie algebra of G2, if we knew it was a Lie group, which we don't yet, but right, we don't know it's a Lie group yet, but if it were, then its Lie algebra would just be the set of X in the Lie algebra of GL7R, which I remind you is just the 7 by 7 real matrices, such that sigma of X, with this formula, right, sigma X of phi is 0. Yeah, because I just differentiate the relation above, and that's going to tell me that I get my, that should be the Lie algebra. Okay, any questions so far?
So like we manually define the psi as a free form over there, and then we define G2 to be the stabilizer.
That's right. So you might ask, why pick this one, right? But I'm going to justify that by saying it's the one that enables you to recover the cross product, right? So that's good. Right? But anyway, I'll come back to that question later. But for the moment, I've picked some very special three form, which is the scalar triple product, if you like. And then I'm looking for the stabilizer of that three form, and that's going to be, I declare that to be G2. Now I'm going to cheat slightly, and I'm going to assume the following lemma, which is that this set of matrices is connected. So I'm not going to prove this. So we're going to assume that that this is a connected set, and now, well, it's obviously a group because it's a stabilizer of something, so it's a connected group. But now I can prove the following proposition, which is that G2 is a compact embedded the subgroup of SO7. So if you look in the notes that you've been provided, the way that G2 is defined is as the connected component of the identity in the thing I defined. So that's the other way you can cheat. You can define G2 just to be connected, right? But in fact, it is what I said it is, and it just turns out to be connected. Okay, so what's the proof? Well, if A is in G2, then, of course, A preserves phi, but that means that A preserves the inner product, because that's what I said there, right? Phi determines the inner product. So in particular, it preserves the inner product. Oh, sorry, A. A preserves the inner product. That means that A is in O7. But G2 is connected means that G2 is contained in SO7. Now, G2 is closed because it's a stabilizer, right? And it's a compact, we're inside a compact set. So if I have some sequence, I can take the limit and it will stay in the stabilizer. So this is a closed set. G2 is closed and SO7 is compact. That means that G2 is compact embeddedly subgroup. By our theorem, right? We had a theorem that said if you had a closed subgroup of a Lie group, then that's the same as the embedded Lie subgroups. So that's what we're bringing to bear at this point, which is very nice. Okay. Is that okay? Great. So now the next thing I want to do is I want to try to get a handle on what is the dimension of G2. I don't know yet. It's something, right? I don't know what, and what should be the best thing I should do? I should try to compute what is the dimension of the Lie algebra, because those will be the same thing, right? That's what I should do. But how am I going to do that? Well, the trick is I want to do what one might call dimensional reduction. I want to somehow split G2 up into pieces that I understand. So I don't understand G2, but I understand some other things. And this is a very nice fact. So let's let SO6 be the stabilizer of the vector E1 contained in SO7. Right? So I look at all the matrices that fix the first vector. Okay? So they look like 1 and then some SO6 matrix. Right? And then I let C3 be the span of E2 plus IE3, E4 plus IE5, and E6 plus IE7. So what have I done? I know that I've now split my R7 into R plus R6, but that R6, I'm thinking of it as C3. Then the claim is that this means that if I look at SO6 intersect G2, it's actually SU3 using these identifications. Right? SO6 is the things acting on E2 up to E7. I intersect with G2 and I get SU3, the SU3 transformations on this copy of C3. Does it make sense? If you prefer, I can say isomorphic too.
When you get all of SU3?
Yeah, I have to prove it. I'm not claiming that it's, I have to prove that this is true. Right? This is the proposition. I have to prove this. Right? Yeah, proof. Let's see. See why it's true. So let's take what we observe is the following nice fact. Ah, yeah, it's like I planned these things. So we see we have an explicit formula for phi up there. So let's let omega be E23 plus E45 plus E67. So that's like the first three terms, but with the E1 missing. And I'm going to let big omega be E2 plus IE3 wedge E4 plus IE5 wedge E6 plus IE7. And what you can spot, I'll just keep it on the board for you for a second and give you 2 seconds to realize that if I look at the real part of this omega, what will I get? I'll get 2, 4, 6, minus 2, 5, 7, minus 3, 4, 7, minus 3, 5, 6. I get exactly those 4 things. Right. Okay? So now I can move it out of the way, and you can believe me, this means that phi, well, you don't have to believe me, I proved it, right? E1 is omega plus the real part of big omega. Okay? Now, if I let J be multiplication by I on C3, then we see that omega of u and v, so it's just immediate from this formula, omega of u and v for u and v in C3 is the inner product of ju with v. Right? Because I'm going to take, it's going to take E2 to E3, right? And this is going to take, this is going to be E3, right? So then if I do E2, E3, I'm going to get 1 from this formula. Make sense? Because if I put U to be E2, this to be E3, J of it will send E2 to E3, because multiplication by I, right? And then this will just be the inner product of E3 and E3, which will be 1. Okay, so that's going to be true. And so you see, if A is in SO6 intersect G2, well, then this implies that A preserves omega and the real part of omega, right? Because I'm stabilizing the E1, so I have to preserve the little omega and this one. Right? I have to preserve both of those. So what does it mean for A to preserve omega? Well, A preserves omega if A is in SO6 and A preserves omega. That's going to be, well, it's already preserving the inner product, so it has to preserve J. So this is if and only if AJ is JA. This is the only thing it can be, but that's the same as saying that A is in U3. Once you identify R6 with C3. Is that, you have these real blocks, but they turn into complex blocks. That's all that I'm saying. All right, now we have to compute what does it mean to preserve the real part of omega. So let's do rho of A omega. Okay. Now for A in U3, because we know that we're a subgroup of U3 now. If I take A in U3 and do rho of A omega, well, it's not too hard to believe. Now A is a 3 by 3 complex matrix. What does this look a lot like? It looks like a determinant type expression, right? It's the wedge of, it's a top form in C3. And so this thing is going to be the determinant of A times omega. So it's a calculation you can do, but it's very believable by the definition of the wedge product. Therefore, A preserves the real part of omega if and only if, well, I can take real parts here. I need the determinant of A to be 1. But that's it, right? That's the end. Is that okay? Yeah, go for it.
Would you mind explaining again why AJ equals JA?
Yeah, I mean, you have to do the algebra here, but in some sense, this is what it means, because you're basically trying to say, you're changing from, you think of something in SO6 and you're trying to think of it as a complex matrix. So you want to say that, so for SO2 this doesn't say anything, right? Because it's going to commute anyway. So SO2 is the same as U1. It doesn't say anything because the group is abelian. But if I have something in, say, SO4 and I want to think of it as something in, I want to think as something in U2, say, then what this is saying is that each of the blocks in SO4, which are just real blocks, they actually split into 2 by 2 things which look like complex numbers. So they look like, cos theta minus sine theta, cos theta. They have to respect the multiplication by I. Said another way, what I does a 90-degree rotation in this plane, right? And a 90-degree rotation in that plane, and a 90-degree rotation in this plane.
J, which is the multiplication by I, as a matrix in R6.
Yep, as a matrix in R6, which rotates each of these by 90 degrees. And because I have to respect, what it's saying is that A then must split, respecting that splitting. So in a general 6x6 matrix does not respect that splitting, but I can split it into 2x2 blocks. That's what this is saying. And once I do that, those 2x2 blocks they're all going to be of the form something like, you know, A, B minus B, B, like this, which I can think of as A plus IB. That's the idea, right? All of them will look like that. That's what it means to look like this. But of course, in SO2, this is saying nothing because they already look like this. But in higher dimensions, this is saying something. And so then you will get that they all look like a complex number. They're all in the span of matrices that look like this. Right? And then you'll see that the condition that A transpose A is the identity becomes A bar transpose A is the identity for the other matrix. So this is an equivalent way of saying what U3 is. In fact, you can define U3 to be this thing. That's how some people define U3, is say it is the real 6x6 matrices for which this is true. You know, a special orthogonal matrix for which this is true. But that's cheating. I don't want to do that. Okay. Okay. So now we have a compact embedded Lie subgroup, and we know its intersection with SO6 is SU3. This is going to help us a lot because now we can compute what is the Lie algebra of G2. So we know it's an embedded Lie subgroup, and we know that its Lie algebra is this thing. Right? Its Lie algebra is this thing. So that we know. So now I need to compute what is the dimension of this Lie algebra, and then I know what the dimension of the Lie group is. So here is the proposition. It says that G2 is R6 plus SU3. So it splits into a 6-dimensional piece and SU3. And so that means that G2 is a 14-dimensional Lie group. It implies that the dimension of G2 is 14. All right. Okay. So how are we going to prove this? So I will just scroll that one down again so we can see what we have to do. So the proof goes as follows. What I want to do is I want to identify this R6. That's what I want to do. That's my goal. And then the complement of that will be SU3. That's what I want to do. So what I want to do is I'm going to let Eij in little SO7 be, they have to be skew symmetric 7x7 matrices, and I have to tell you what their KL entry is, but it's going to be 1 if KL is Ij, minus 1 if KL is Ji, and 0 otherwise. The sort of elementary basis, the simplest basis you can think of for SO7. Okay, so now what I want to do is I want to say, well, let's consider E1J. I'm going to consider these. In particular, let's look at sigma of E12 acting on phi. Right? I want to compute this thing. And you may think, oh, wow, that's really hard. But it's not, because all you have to do is, what is the action? It just swaps 1 and 2. That's what E12 does. It just swaps 1 and 2. That's all that it does. So I just look at this formula, and it changes the sign. It sends 1 to 2 and 2 to minus 1. That's what it does. So here, it sends 1 to 2. Well, that's going to give me 0, because I'm going to have 2, 2. Right? So that I throw away. It's going to send this one to a 2, so I'm going to get E245. The next one, it's going to send the 1 to a 2, so it's going to be E267. And then it's going to send the 2 to a minus 1, so minus E146. And it's going to send the 2 to a -1, so plus E157. Okay. So yeah.
Why does the first one vanish? Why aren't we just changing the one to two?
No, because you change 1 to 2, but you do it each. Yeah. So if you look at the formula, right, I do it one at a time. I don't do them at the same time. I do it one at a time, right? So I change the first 1 to a 2, then I change separately. I change the second 2 into a -1. So both times they cancel. Right? Both times I'm going to get a repeated index, and I get 0. Okay, that's what's happening. Because I do it one at a time. Sorry? 3 doesn't do anything. 3 is fixed. This only acts on 1 and 2.
So we have E223 and then E.
Well, E223 is 0. So I'm going to get E223 and minus E113, but they're both 0.
We don't have a third term? Like we don't have...
No, because we're only swapping if there's neither 1 or 2, I get 0, right? It's 0 otherwise. This thing will map the vector to 0. It sends E3 to 0, right? So if I have a little E3, that'll go 0. Everything else goes to 0. That's what's going to happen. And then what you can compute, okay, well then this takes some thought, but you can sort of see that maybe the smart thing to do is E45 plus E67, because they're here. 4, 5 plus 6, 7, it's there. Kind of makes sense that one should do it. And if you do it, then what you get is 2 times E146 minus E157 minus E245 minus E267. If you do it, sorry, times phi. And so what that means is that if I do 2 E12 plus E45 plus E67, this is an element of G2. Because if I do 2 of these plus this, I get 0, which is what I wanted. Remember that my G2 was the things such that sigma of x of phi is 0. So I found an element in the Lie algebra. And what you spot, what's nice about this formula is that something of the form E1j only appears once, right, at the start. I get an E12 and then all the rest don't have 1s in them. So what that means is that each of the E1j's will give me a unique element in G2. Right? They can never coincide because there's never, the E1j won't appear again. So what this means is similarly, we get that E1j defines, so similarly we get that E1j defines unique element in G2 for each j, but which j's can I choose? I can only choose 2 up to 7 because E11 is 0. So I'm going to choose 2 up to 7, and this gives me an R6 subspace inside G2. So then I can restrict to the span of the Eij such that I and j are in 2 up to 7. Right? Because I've got rid of the ones with a 1 in them. I've got rid of all those. But what is this? That's SO6. And I know that SO6 intersect G2 is SU3. So that means that SO6 intersect my G2 must be little SU3. So SO6 intersect G2. In fact, it's this same SO6, right? This SO6 is the Lie algebra of the SO6 I defined before, the stabilizer of E1. It's the same SO6, and I know that SO6 intersect G2 is SU3, so that gives me the result that I said. Yep?
Would you mind repeating the argument why you can generalize finding this one stabilizer to finding 5 further ones that look?
Yeah, you just do 1, 3, and then you'll get something that doesn't involve a 1 in it again. So it must be independent of this one. I mean, okay. I mean, yeah, you don't know. As I said, similarly, it will work. I mean, I claim that it will work, right? I mean, it's true because if you take 1 something, basically it's from the algebraic form of this. If I take something of the form, say, 1, 3, then this one will go away, and you'll see I'll get these guys, right? I don't have 1, 3 only appears once. And this can have, that's each pair only appears once in this formula. So you'll never see it again. Right? You'll never see anything with ones. All the ones here will turn into 3s, right? And all the 3s here will turn into 1s, but there'll be nothing of the form that you had before. So it works, but I mean, one has to do it. Right? Yeah. Okay, so this is it, right? So now I hope you can believe me that G2 is 14-dimensional. Now, I want to do an observation, which is that if you look at the orbit of phi, so this is the orbit stabilizer theorem. Hopefully you remember this one. So I'm looking at the orbit of phi. So this is going to be the dimension of the whole group, which is GL7R. So this is GL7R, is isomorphic modulo the stabilizer of phi, right, by orbit stabilizer theorem. So I can compute the dimension of the orbit. The dimension of the orbit must be the dimension of GL7R minus the dimension of the stabilizer of phi, which is of course the dimension of G2. So this is the dimension of GL7R, which is 7 squared, 49, minus the dimension of G2, which we just computed was 14. So that, if I can do maths, is 35. Why is that significant? Why is that number significant for us? Do we know? Why do we care about this number? This number is 7 choose 3. That's another way to think about it. Does this help you? Enough hint? This means that it's the same as the dimension of the whole space of 3 forms on R7. So the orbit has a chance of being an open set in this vector space. Right? Has the same dimension. So there's a good shot that it's actually an open set in the vector space, and that's actually true. So this is a proposition that I won't prove, but it's true that the orbit of phi is open in lambda 3 R7 star. And for all gamma in the orbit of phi, the stabilizer of gamma is G2 again. So what this means is that actually, even though I picked a very special 3 form to define G2, there's an entire open set of them, which all have stabilizer G2. So in fact, it's actually a generic condition. If I pick a 3 form at random, with probability 1, its stabilizer will be G2. 3 form in R7. Okay? Which is a bit surprising when you first see it, because it seems very, very special. But then in fact, it's an open condition. Basically, any 3 form will work. Okay, now I'm going to tell you something more about the algebra. So here's the lemma that the rank of G2 is 2, and the roots are plus or minus x1 minus x2 plus or minus x2 minus x3 plus or minus x3 minus x1 plus or minus x1 plus or minus x2 plus or minus x3 with x1 plus x2 plus x3 equals 0. And so here is the proof of that. So the proof of that is just that if you take T to be the maximal torus in SU3, so that's going, then T is contained in G2, and G2 splits as R6 plus little SU3, and this R6 you can identify with C3, and the weights of T acting on the C3 are plus or minus x1, plus or minus x2, plus or minus x3. So they're just the usual, it acts in the standard way on that C3, right? As e to the I 2 pi I x1, e to the I 2 pi I x2, e to the I 2 pi x3, diagonally. So that means that this thing splits into T plus this C3 plus the GA, the sum of the A, GA, where these are the irreps for SU3. And this is an irrep. So that means that T is a maximal torus in G2. And the roots are as claimed. Are as claimed. Because it's the ones on SU3 plus the ones on this C3. And no more. Is that all right? It's just the same ones that we had. Is it okay? Yeah, good. Next thing, what is the Weyl group of G2? As I said, we're trying to pull everything together, right? So we should try to compute what that is. So the Weyl group W of G2 is so exciting it killed the pen, is the dihedral group D6. And the proof is that this Weyl group, it must embed in O2 because G2 has rank 2. So it must embed into O2 and is reflection in what? Is generated by the reflections in the root hyperplanes, but there are 6 of those. So in the 6 root hyperplanes is generated by reflection in 6 root hyperplanes, but this must be the symmetries of a regular hexagon, which is D6. Because we're just in the plane, we've got 6 root hyperplanes, we're reflecting in them, so it must be the symmetries of the hexagon. It can't be anything else. And then the last thing is the following proposition. Oh no, 2 things. G2 is simple. So I said that it was, but why is it? Let H contained in G2 be proper ideal, but then H and H perp are going to be proper ideals and reps of SU3 because SU3 is contained in G2, so there'll be representations of the smaller group, SU3, but this is going to imply that H and H perp must be SU3 because SU3 is simple, so this uses that SU3 is simple, must be SU3 and R6. That's what they must be. We know that G2 is SU3 plus R6. There can't be anything inside the SU3 part because SU3 is simple. So there has to be all of this. Then it has to be the orthogonal complement of that, which is R6. It's the only thing it can be. But R6 is not a Lie subalgebra. So that's a contradiction. You can show that this R6 is not a Lie subalgebra, so it definitely can't be an ideal. So it has to be everything. So G2 is simple. And then the last thing, well, second to last thing, again, I'm going to cheat. And I'm going to say that it's true that G2 is simply connected. So it deserves to be on the list that I gave last time. All right. There's one more thing we should do before we finish this lecture. And that is we should try to understand what are the representations of G2. Right? What is the representation ring of G2? Right? That's what we should do. And then we really will have finished the story. Because then we'll know everything about G2. Well, not everything, but we'll know a lot, right? We'll know its dimension, that it's compact, that it's got what its Weyl group is, that it's a simple group. But we need to know what its representations are, its irreducible representations are. And that's the following theorem that says that, a proposition that says that the representation ring of G2 is the integer combinations of sigma 1 plus sigma 2 and sigma 1, sigma 2, where these are the elementary symmetric polynomials. Okay. So let's prove this to finish. Okay. So how are we going to prove this? So these are the elementary symmetric polynomials where sigma 1, sigma 2 are the elementary symmetric polynomials on T1, T2, T3 such that the product of the T's is 1. It's because that's what our maximal torus is, right? It's T1, T2, T3 with the product is 1 because the determinant is 1. Okay, so here's the proof. So you know that we have an injective map to the representation ring of T invariant under the Weyl group. We know we have this. And this maximal torus, we already know that R of T S3, so this is the same as the representation ring of SU3, is the ring generated by, it's the integer things generated by sigma 1 and sigma 2. We already saw this, right? That this is true. But what's the extra element in the Weyl group? So W contains another reflection, an extra reflection. And what it does is it sends T1, it sends each Tj to its inverse. That's what the extra reflection does. It's just minus, it sends all of the xi's to minus themselves, so it does this. This is the extra reflection. Therefore, it maps sigma 1, which if you remember was just the trace, T1 plus T2 plus T3. It maps to T1 inverse plus T2 inverse plus T3 inverse. Well, that doesn't look very good, but actually, that's sigma 2 in disguise. Because T1 times T2 times T3 is 1. So you can make a common denominator of T1, T2, T3, and you'll get T2, T3 here, plus T3, T1, plus T1, T2, which is exactly sigma 2. So in fact, this is the same. Yep?
Sorry, what do you mean when you say W contains an extra reflection?
Yeah, because I can think of D6 as being like S3 plus one more reflection, right? I can permute things around and I've got one more reflection that I have. Right? And this is how I can generate. There's one more generator, and then I get the same, then I get the group. And so that means that R of T W is going to be the thing that I said, this one. This will generate R of T W. And so then I need to prove that this map, which is an injective map, is actually surjective. And then I'm finished, right? This is our standard trick, right? We know this map is injective. We know what this thing is. We can always compute it. And now we need to prove it's surjective. So all I need to do is find two representations so that I get any combination I like of sigma 1 plus sigma 2 and sigma 1, sigma 2. And then I'll be done. So this is the end. So I say that if I take the standard representation of G2 on R7 and complexify, because remember that when I do the representation ring, I always have to complexify my representations, right? I always have to complexify them. And so this is going to be, I'm going to call this V7, which is R7 tensor R over C, is going to be C plus C3 plus C3 bar as irreps of SU3. And so you can compute that the character of V7 restricted to the maximal torus is just going to be the one for SU3. So it's going to be a 1, because this is trivial, plus T1 plus T2 plus T3, because that's how it acts on C3, right? Plus T1 inverse plus T2 inverse plus T3 inverse, because that's how it acts on C3 bar, right? It's by the conjugate. But that is 1 plus sigma 1 plus sigma 2. And then you can also see, because V14, which is the complexification of G2, is going to be C3 plus the complexification of SU3, this means that the character of this representation is T1 plus T2 plus T3 plus restricted to the maximal torus is the same as the character of SU3 restricted to the maximal torus, which we computed. And this is going to be sigma 1 plus, sorry, I messed up here. There's also a C3 bar. Sigma 1 plus sigma 2 plus sigma 1, sigma 2 minus 1. Right, because this was the one for SU3, and this is the one for the C3 plus C3 bar plot. And so we've got everything, right? And so it's true. So there you have it. So now we know everything about the group G2. And we've managed to pull together almost all of the theory that we have seen in this lecture course into this final lecture. And with that, I will finish. Thank you very much.